Previously, I was talking more about the analytic properties, the mathematical properties, Euler equations, and why they are so intimately related to this finite volume interface. Now we'll look at something more ancient, older than the finite volume method, which is the finite difference method. It's still very popular for a lot of other applications. So in finite difference approach partial differential equations, partial differential equations are floats in the heart of continuum models, and actually a lot of other things as well. So the idea of finite difference approach is to replace the differential equation with difference equations. Okay, so basically you're discretizing the continuum problem. So these are, and we've already seen these, the wave equation and the diffusion equation. And these are initial value problems. So you have an initial condition, then you have boundary conditions, and you're evolving them in time. We have encountered this. This is Poisson equation. Here, you are given values of rho at the boundary, and you are solving for rho, which satisfies this equation everywhere. So there's no marching in time. It's just given the boundary conditions, you're solving for psi. So this typically leads to a matrix equation, which needs to be solved, and typically it's solved iteratively in postmodern methods. But we'll not be talking about this. We'll talk about this only because finite hyperbolic equations is what we are dealing with. Okay, so the finite difference approximation to derivatives. And this is all like extremely simple in this approach. It is based on Taylor series expansion of a function f near some x and t x naught t naught. Okay, so these are Taylor series formula, but remember Taylor series breaks down at discontinuity. That's why the finite difference methods are not as successful in dealing with shocks and stuff. It's discontinuity. It's not. It's derivatives infinite. But anyway, let's see how far to go with this approach. These are standard Taylor series expansions of f(x, t) around x naught, t naught. So this is the f dot here is the tensor derivative dow f dow t evaluated at x naught, t. F prime is dow f dow x evaluated at x naught, t. You all know it, and so on. You just keep on going. Now, if you're given, you can write fx plus delta x comma t is equal to. So, here I'm using t as t naught. It's obvious what I'm doing here. I'm just sort of expanding f in x and taking t to be constant. Some simple. Similarly, I can hold x fixed and expand it in time. Okay, so this dow f dow t evaluated at x naught, t naught, or xt is just this is the definition of that derivative in the limit delta t goes to 0. But here we are actually calculating with a finite delta t. This is the difference form. And if you look at the Taylor series, and so this, the now f dot is just f dot, right? So f dot is equal to fx comma t minus f x naught t naught divided by t minus t naught. Then you'll have these time terms. Basically, this is what you're doing. Right? So you will have the term. So this is f dot. So this minus this divided by delta t is this guy, and you have the first term when you divide by delta t. It's an order delta t error in this expression. Okay, so this is the finite difference form. Similarly, dow f dow x, you can write in this form, and using this Taylor series expansion, you know that the error here is order delta x. So this is forward difference, right? You're taking t naught plus delta t and subtracting t naught. So it's forward in time. This is forward in space. Now you can actually do better. You can do something called center differencing, which is done here. So you take f x naught plus delta x minus fx naught minus delta x and combine them. So just write an equivalent expression for fx minus delta x comma t. So it will have a negative term here. This will still be positive and so on. If you combine them, then you can actually show that the order there is delta x squared. So this is a better approximation for smooth f's. This is a better approximation than partial f, partial x. This one, the first order thing. We have already encountered the advection equation. This is another form. Whatever the initial waveform is, it just gets translated. Again, this I've used a different notation. Earlier I was using U, but I'm using F. In fact, F I was using for flux. But grow up beyond these little things and try to understand the gist of this. So V is the advection velocity constant. We have done this. This. So this is t equal to 0. This is some later time, much later time. Same thing as moods. Okay, so we looked at this equation, looked at characteristics and so on. But now we are just doing finite difference. We're really not thinking so much about connecting with the physical content of the equation subsets. So this is the advection equation, dou f dou t plus b dou f dou x 0. Let's just write forward time, forward space, difference approximation for this PDE. I told you, the recipe to convert partial derivatives into differences. So you need to apply forward in time. So this is the forward in time difference approximation for dou f dou t. This is forward in space approximation for dou f dou x, and you'll have term order delta t delta x error in this expression. The good thing is, as you make delta t and delta x 0, the right hand side goes to 0. So that means this is a consistent formulation of the equation. So in fact, if you go deeper into the theory and proofs in numerical analysis, the equation has to be consistent and stable. So if you have a numerical scheme which is consistent, that is the finite difference approximation goes to the differential equation that you want to solve. If the scheme is stable, then you'll get converged answers. Basically, if you increase your grid resolution, you'll start approaching the right answer. Okay, so this is forward time, forward space. This is forward time, centered space. Homework problem. These are extremely simple, but it's worth doing it because that's when you learn. Even this is sort of trivial stuff. Now, if you look at this expression, we want fin plus 1. Okay. Now, you can rearrange it and write it as fin plus 1 equals fin plus 3 delta t by delta x difference this. So what do you see that fin plus 1? So you actually see these space-time diagrams again. So this is x, the y-axis is. This is I comma n. This point, this is the present value of f now here. Okay, so fi. So this is fin plus 1. So n plus 1 point at the same location. This is fin plus fi plus 1 again. So this is this point. So what this is suggesting is that this point in the next step only depends on the value of f here and here in the previous time step. Okay, so this is called a tensor. So you have a grid in space and time, and how the solution of n plus 1 depends on solution of n and n plus 1. This is called a stencil of dependence of the solution. So this is forward time, forward space stencil, and this one is forward time centered space. So you can actually see f at in plus 1 depends on fin, which is this point. So this is fin plus 1. This is fin. This is f plus 1. This is fi plus. So the solution here depends on this point, this point, this point in this single time step. Okay. So this is sort of like numerical zone of dependence, Yeah. So I actually gave in the previous talk, I gave you this example of range of influence and zone of dependence. This, the solution here depends only on this point, this point, this point. So this numerical zone of. Okay. One such technique for analysis of numerical streams is something called one-on-one stability analysis. This is a linear analysis, basically. And so if you have a difference equation, for example, here the FTCS scheme for reflection, what you do is, so your xi is equal to I delta x, so 0 for x1 is delta x, and x2 is 2 delta x. So you're basically labeling the grid. If you, what you say is, I'm actually looking at a particular Fourier mode, and you write fi comma n is equal to function of time, which is rt here, the function of time, and the spatial dependence is just e to the ikx. I think it's like a plane wave. Because here actually j is I, this minus square root of minus of the complex I, and I is the grid label. Okay, so if you substitute this form in this difference equation, what you'll get is what would be the evolution particular Fourier mode with wave number k. So this, if you substitute here, so you'll get RT e to the, so this is at fn plus 1. So n plus 1 is equal at I is just R times this, right? The time dependence is only this. So at every time step, your previous value gets multiplied by R. Okay, so fin plus 1 is R times fin. And fin itself is this. So if you substitute that and cancel, e to the I, stop, you get this equation. And you can solve for R. For that particular Fourier mode, how does this initial k mode, grow in time or decay in time? We know the physical solution, right? There is, the modes are just vector, they don't grow. They just have a change of phase. The phase is added with time. Their growth is the growth and damping is 0. None of the k modes grow because it's the same shape, just a vector. Good. Now, if you have this equation, you can actually solve for R. Right? So that tells us how much, by what factor does your value for a particular k mode grow in a single step. And R better be, mod of R better be less than or equal to 1. If mod of R will be a complex number in general, because this is a complex number. So if mod of R is greater than 1, what it means is that some of the modes are amplifying. And this is numerical instability. So in 10 time steps, you'll get mass. Okay, in reality, when you encounter this. So it's very easy to tell when you encounter this. Okay. So this is just the representation of these Fourier modes. So if you have a domain of size L, the possible values of k are 2 pi n by n, where n equals to 1 is this mode and this mode and so on. And the k maximum value, the largest k that can be represented on this grid is L by 2 delta x. This corresponds to this Nyquist wave number. It is this. Okay.
So we can only use this one stability for linear systems.
No, you can use it for nonlinear systems, but it will just give you linear behavior around that initial condition. Can I comment on the Nyquist mode? Right. So, so the Nyquist mode is actually. So suppose you have a grid. Okay. If you have a value here and a value here, so I'm sort of drawing my thing. This is one of my k modes. This is the highest k that I can represent. I cannot represent this, for example, on my grid. If you have a wave which is varying like this, I have no grid points to resolve it. So this is the highest case. So this is lambda corresponding to the Nyquist mode. And this is just 2 delta x. So lambda is equal to 2 delta x. So k equals 2 pi by lambda, which is pi by delta x. Okay. So this is called, so, this is a very common thing. Like when you do radio astronomy, you're doing Fourier transform, when you're looking at different k's. This Nyquist is basically the highest grade number or highest frequency that can be represented on a finite discretized stereo. Okay. So if we proceed in manipulating this equation, let's see.
I have one question.
Yes.
Is it possible that for some algorithms the error in say long spatial scales grows exponentially? It's unstable in long scales, but not in other modes.
Yes. This R is the general function of K. Yeah, absolutely. So this is basically, if you write e to the j delta x as cos, Euler identity, e to the ix equals cos x plus I sin x, you get this. Okay, and you can 1 minus cos k delta x is, you can do this. Okay, so this is a complex number. So this j part represents the phase. Right? The evolution introduces the phase difference, which it actually should, because advection corresponds to a phase change. But it should, the correct value of R should have an imaginary part which is 0. It should not grow or down. So, but you can actually see that this is not the case. Usually, error is larger for the highest K mode, because you're not representing that wave as nicely. If you have a small number of modes, so the largest error is for largest Ks. And you can actually see if you make a K small and you do a Taylor series of signs, you get the right answer. So if you take the mod of this complex number R, this is called amplification factor. You can just, this is the complex number. Just this is the real part. This is the imaginary part. Real part squared plus complex part squared, square root of that. That's R, but this is R squared. So this is just this. Okay. So what you see here, this has to be less than 1 if your numerical scheme is stable. Okay. If your V is positive, you can actually see this is greater than 1 for all J's. If V is greater than 0, then this is unstable for all J's. So it's extremely numerically unstable. But if V is negative, then actually, it can be stable. Okay. So you can actually show that this forward time, forward space scheme is unstable for greater than 0, and it's stable if V delta t by delta x is less than 1 for negative velocities.
Which could also just mean that so it's stable if you're simulating it backwards in time.
Or it's stable. See, we know the advection equation, right? Information propagates in this direction for positive velocity, whereas the different thing that we are doing is the opposite kind. So, physically you anticipated that this would be a problem case because, characteristics are with a positive slope. So how can you use this value to calculate the derivative? It should really depend on the left side. So that's why the negative velocity is stable for a small enough delta t, and this one is unstable for any value of delta t. So this is the idea of upwinding, which I'll come to in a minute. So this, okay, so this is homework. Via von Neumann stimulated analysis show that FPCS, so this what we are doing here was FPNS, forward time, forward space. You can actually show that FPCS is always, whatever the delta t, unstable. Okay, and that's also possible because propagating information from both sides, and one of them is definitely unphysical, irrespective of the direction. Okay. Now this brings us to this important thing called the CFL condition, Courant Friedrichs level condition for the stability of these finite density volume, finite volume metrics. Now, what it says, so this is your XT grid, the numerical discretization. So you have some solution at this time Tn, and you want to take a step in time. The larger the step that you take, the faster you are able to do your computations. But if you take too large a step, you can have numerical instability. We just saw that. Okay. Now, so for example, here on the left, I have shown to take a small delta t, and if you just, this is the zone domain of dependence. So here, things can be affected numerically from whatever is happening here, right? If something is happening here, by this time that information hasn't had time to propagate to the point of interest. Right? So what this is telling us is that only this, in the previous time step, only the one left point and one right point, the central point, are the ones which can affect the solution here. Right? Because whatever happens here can even affect it here because it's not causally connected. So what CFL condition, this condition that we got from this one-normal stability analysis corresponds to is that in order for the steps delta t that you should choose in order to be numerically stable should satisfy the fact that the new point should not be in causal connection with the points which are beyond the nearest neighbor at time t ends. Okay, so this is the unstable situation shown. You see information beyond these points are traveling, and that results in numerical instability. So this this condition of CFL, the CFL condition that B delta t by delta x, where B is the characteristic velocity, should be less than 1, is a necessary condition for stability, but not sufficient. We've already seen it. Right? We had this FPCS scheme, which I gave you as a homework to show that it's unconditionally unstable. That even if you satisfy delta t to be less than this, your numerical scheme is unstable. So this is a necessary but not sufficient condition for stability. Okay, so these are like classic, these are old methods. These, you will hear Max's name a lot of times. He's one of the fathers of. He was a mathematician. He actually is a mathematician. He's like in his 90s, such a number. He has a lot of results in the formal proofs and so on, but also some numerical methods that he helped invent. So this is the FTCS scheme, okay? So this is unstable. I already told you. Now what you do is instead of FIN, if you replace it with I plus FI minus 1n, so just by trial and error. With this, if you look at the Taylor series expansion, this is a second order accurate approximation for FIN because it's a centered average. So this new expression, which is the Lax-Friedrichs scheme, has this form, and this is the stencil. So the solution here does not actually depend on FIN. You can actually see this point does not affect the solution. There is no dependence on FIN. It depends on FI minus 1 and I plus 1. So, and you can actually show, this is another homework problem, show that the Lax scheme is stable for if you satisfy the CFL. These are actually extremely simple. This actually, everything that I'm talking about in the context of finite differences, a lot of them have analogies with finite volume. Because they're also very related methods. So there is another way of looking at the stability of these conditions using the partial differential equation itself. So for example, this is your FTCS scheme, the difference scheme. Now, what you do is write out the equations that these are evaluated. So Fin plus 1 is equal to Fin plus delta T F naught plus T squared by 2 F naught and dot dot dot. If you plug that in here in terms of F dots and F primes, you can get what this finite difference equation is approximating. Which PDE is it approximating? So this is equal to 0 is the leading order equation that is approximating. So if you put delta T and delta X to 0, you get the infection equation. But if you retain the first error terms and write it in terms of F double dots and F2 primes, you have this. Okay. This is very handy. Now, whenever you're doing this analysis, you want to write the time derivatives in terms of space derivatives. They're very right? F dot plus B F prime is equal to 0. So you can write F double the spatial derivatives. You're not F double is writing in terms of spatial derivatives. It's this in terms of a spatial derivative. If you do that, you get this equation. So F double dot will be written in terms of it. So anyway, this is higher order. This delta X squared. This is delta T. So this will be smaller than that in general. And we already saw in the CFL condition delta T is proportional to delta X. So this is a higher order term. Okay. Now, if you look at this equation, essentially the leading order error, the leading order term on the right hand side is this. And does it ring some bells in someone's head? It's not a diffusion equation. It's an anti-diffusion. It's a negative diffusion equation. It's a negative term. Diffusion equation is partial F or partial T is D N squared F. This is negative diffusion equation. Anti-diffusion equation is imposed. So it's not a well-behaved equation. That's why things can just grow and become infinite. This is another way of looking at why FTCS is numerically unstable. You can actually do the same for all these different schemes. And if this is lax scheme or this lax Friedrich scheme, and this is the equivalent thing. And here you can actually see this is diffusion if delta T is less than delta X by the CFL condition. It's a diffusion term. This has a positive coefficient if you satisfy the CFL condition. Otherwise, it's anti-diffusion, again, unstable. Another way of looking at the stability of these finite difference schemes. You can make these schemes higher order. The lax schemes can be made higher order. So you see, question?
So, sir, if you see the right-hand side of the modified equation for lax Friedrich scheme, as delta X and delta T whether tending to 0, it might not be consistent.
You're assuming delta T and delta X to be proportional.
Yes.
Right. So then, so this is order delta T, that's order delta T.
Yes.
Right. So this is consistent, right? If you make your delta X and delta T going to 0 such that delta X and delta T are proportional to each other, this goes to 0. Right? If you make a delta X and delta T go to 0, keeping delta X proportional to delta T, this goes to 0. If this is delta T squared, and this is delta T.
There can be conditions where it might not be consistent.
If delta, in the limit delta X, delta T going to 0, and not like, delta, these are not independent. If I have a fixed CFL number, delta X squared is K times delta T squared, right? So, if the equations are not consistent, you just abandon that right there. If they are consistent, then there may be some hope. Okay, so the Lax-Wendroff, so this scheme, forward FTCS or Lax scheme is only first order accuracy time. You want higher order accuracy. The classic way is something called Lax-Wendroff method, in which case of the first step, so you estimate the value of F at I plus a half, 1 plus a half. Okay, and this is a Lax step. Okay, this is just the Lax evolution scheme for time delta t by 2. And I've written this Bf as a flux, capital F in this case. So Fi n plus 1. So this is, this is the first step of it. This is the next step of it. Okay. So you calculate this F at n plus a half, I plus a half, and then you put F into the flux expression, and you do this difference. Now, this is centered in space and centered in time. Because this evaluated at F plus half. Right? So this scheme is through Taylor series. You can also show it second order in space and time. Okay, good. Now, if you do this modified equation analysis, you see this is the leading order error. And there's F triple prime here. Previously, we had things like F double prime, sometimes it's positive coefficient, sometimes negative. Here, this is F triple prime. Now, if you take F's to be complex numbers, F triple prime corresponds to a phase error, right? So you have E to the ikx. Prime gives you ik e to the ikx, that's 90-degree phase shift, right? And double prime gives you ik the whole squared, which is not a phase error, it's an amplitude error. So this triple derivatives, first derivatives in this, or fifth derivatives, give rise to phase errors. So you can actually see that in the nature of the solutions involved with this, that it will give rise to phase errors. This is the idea of upwinding, that if you are solving the invection equation, if V is greater than 0, then you should really use this tensor, Fi minus 1 divided by delta x. If V is negative, which is this case, then you should use Fi plus 1 minus Fi divided by delta x. This sort of incorporates the fact that information travels in the right direction. You can also interpret this up. So whether this sort of upwinding was invented in the 1920s. This is Courant, Isaacson, and Rees. That's correct. So that's where it goes back. So upwinding is no idea that information people get in the right direction was actually known. It's not like everything was invented in weeks long. But people build on older ideas and come up with better schemes. So this is finite volume interpretation of the upwind method. So you'll have these piecewise constant values, as in this Godunov method based on V1 problem, and you have this initial condition. You just evolve it for time delta t. The evolution of this is just moved by time delta t, which is shown here. These are the characteristics of it. And now we just average this to get the new average value of Q, so which is just this. So this is just a reinterpretation of this upward method in terms of a scalar Godunov method of bidirection. Now these are some, again, the code. So this is I've shared. This I made this. Now this is the initial condition. The blue curve is the initial condition. It has this Gaussian and a square wave. So it has this discontinuous initial condition. Discontinuous initial conditions are important because Euler equation gives rise to discontinuities naturally. So this is not like an artificial rest. So what you see is this is the lax. It has this funny oscillatory pattern, and that's because of this decoupling of Fin. It did not affect In plus 1. You remember the stencil did not take the middle point. That's what sort of gives rise to this funny pattern. So this is lax. This green curve, green dots are upwinding. Just using upwind method, velocity greater than 0, so you use the correct differencing. This pink magenta thing is through Lax-Wendroff. Lax-Wendroff is formally higher order activity, second order in space and time. But if you have these discontinuous initial conditions, it gives rise to problems. And you can actually see the problems. Actually, let me ask, which of these solutions do you think is better? The green one, red one or the pink one? Just I know the colors. Green one, right? But it's only first order accurate. Why do you say so?
This question is quite high in life cycle, which we usually take to.
Yes. So basically, it is non-monotonic. It creates new maxima and minima, and you don't want that. It's going to destroy the solution. So even though it's formally higher order accurate, it's not good. So that's why you should not just be, obsess about higher order accuracy. Robustness and these kind of mathematical properties are extremely important. Okay. This is it. Okay. So by the way, codes are there. You can actually see the phase errors. See here in these two lags and full method, position of the maxima are almost where it's not in with. This is actually, let me tell you what I'm solving. This is the initial condition. I'm solving the direction equation, and the boundary conditions are figured. So this thing, when it moves out on the right, it emerges on the left. And it's done for one period. So the right answer is, it should be on top of the initial condition. Okay. And these things, then you have oscillations behind of this discontinuity are indications of phase errors.
Even for the case of Gaussian function, they were disconnected, they were dispersed, and
They're a little bit it's basically coming from the square wave. If you just had velocity, basically the thing is again it's continuous square wave. If you Fourier analyze it, it has all phase. Right? So that's what different J's propagate with different speeds. You can dispersion of the wave. That's what it is actually happening.
So the advection here is diffusing due to the fact that we are neglecting the higher order terms.
See, advection is diffusing because it has it suffers from amplitude error, not from phase error. So its location of the peaks and so on will be right. It's just that its amplitude will be damped.
So it is sort of related to this numerical stuff.
Absolutely. I mean, all this is numerical stuff. Okay, so now if you have the diffusion equation, how do you deal with it? This is the diffusion equation. So you can actually think of flux also in terms of for a diffusion equation. So F is just minus d W dou x in case of diffusion equation. You can actually see W dou t plus W x of F is 0 if you choose F to be less. That's your diffusion equation. This is also an initial value problem. But unlike hyperbolic equations, here disturbances propagate over the whole domain, as I mentioned previously. If you look at like a Fourier, one of a Fourier series K mode, on the right hand side, you can actually see this just minus dk squared dk. This Fourier method basically represents damping of K means on the moon. In fact, larger K modes are damped more, and that sort of agrees with our intuition that small scale fluctuations are wiped out faster compared to large scale fluctuations due to diffusion. You can actually write a finite FPCS scheme, which is written here. So this is Ujn plus 1 minus Ujn by delta t. So this is the finite difference, second order finite difference approximation for dou to u dou x squared. I'm taking d to be constant, diffusion coefficient to be constant. That can just come out of this. So if you write that, this is what you have. So it's again first order in time because the time difference is centered at n plus a half, not at n. So this is only first order in time and second order in space. Again, you can do the Van Lyman analysis. This is the amplification factor that you get. And you want, so again, for diffusion, you know that all modes get down rather than growing. So if your mod of R is greater than 1, that's numerical instability. And if you look at this expression, that happens at this term, because, this you can sort of ignore. For low k, for k delta x by 2 equals pi by 2, which will be a mode in that family of k's, this is just 1. For d delta t by delta x squared, when it becomes 2, so it will become 1 minus 2 or higher. If this thing becomes 2 or higher, r can become minus 1.5 or things like that, and it will be unstable. It's the mod of r which matters. So it will be, say, if it is minus 1.5, it goes from 1 to minus 1.5 to minus 2. Just so in delta t should be less than delta x squared by 2 delta t from von Neumann's analysis. Again, one would show this. Now, this is actually problematic. This is too short a time step, right? Previously, we had delta t proportional to delta x. Here we have delta t proportional to delta x squared. And as you go to higher and higher resolution simulations, you are making your delta t extremely short, and that's not desirable, right? You don't want to like take tiny steps. You can actually correct that situation if you do a backward time differencing. So instead of evaluating the right hand side at n, you evaluate the right hand side at n plus 1. This is BTCS, backward in time, centered in space differencing of this equation. In fact, this is actually a little different from this equation because here unknowns are there on the right hand side. N plus 1 terms are on the right hand side. So what you do in this case is you make it into a matrix equation. And if you have n plus on the right hand side, you have to bring them on the left hand side. But if you do that, you get a matrix equation. Okay. And this is how that matrix equation looks like if you have periodic boundary conditions. You can do von Neumann's analysis again. Simple, you have R here, R, again R here, and again R here. Right? These are all at n plus 1. And you can actually show that this is R. The value of R comes out to be this, and this you can actually show. So this alpha here is d delta t by delta x squared. And you can actually show whatever the value of alpha is greater than 0. Cool. This is always less than equal to 1. So the nice thing about this implicit method, in which the right hand side is evaluated to n plus 1, is that it's numerically stable for all delta t's, not just for delta. It does not even matter whatever delta is. So this is actually nice. So you want to treat confusion implicitly if you can. The problem with this is you have to solve a matrix equation. Okay, and this is a tri-diagonal matrix in case of 1D, but 3D it's tri-diagonal plus it's a sparse matrix still, but a complicated matrix to solve. So a lot of people actually go to this approach. As I said, the elliptic equations also boil down to solving a matrix equation. So the methods used are extremely similar. Okay. I don't know. So till now I've just talked about.
Pluto also has implicit solvents.
Yes, so Pluto has something. Some Pluto does not have implicit solvents. It has something called super time stepping, which is sort of like a trick that you play. If you have this time step, and if your stability time step is tiny, there are tricks that you can do in which you can take smaller number of sub steps and eventually reach this final step in much smaller number of steps. So it has something called super time stepping. In fact, the most recommended super time stepping there is called the RKL, and it's something that Bhargav and have actually put it in there. So that approach is not an implicit approach. It's an explicit approach, but there's a trick that you can play in that. And that's also very nice from parallelization point of view. It's still like very similar to the other steps of the method. Okay, now right. So that was about finite difference method. So there are a lot of these homework things. You should try to do these because they are not hard. Try to just start to talk to us. Now, if you want to, so if you want to get higher order accuracy with upwind, I mentioned to you about this upwind method, where if mu is greater than 0, if velocity is equal to this difference, if velocity is equal to this difference. But that's just first order accurate. It's not very accurate. So how do you achieve higher order accuracy, like a second order accuracy? So the approach here is something called the RSA approach, which stands for reconstruct, solve, average. It's also stands for REA, reconstruct, evolve, average strategy. So the first step is reconstruct the function defined for all x within the within the zone or the grid, such that its average value should be the same. Okay, but you can actually have like a linear slope and things like that. Then once you have this piecewise linear or piecewise quadratic approximation, then you evolve it. And since we are talking about advection equation, evolution is trivial. You just shift it by v delta t. Okay. And after you've done that shift, you average it. This is your new in plus 1. So the recipe for getting to higher order in this approach of winding is actually to do higher and higher order reconstructions. Rather than piecewise constant, you make it linear, quadratic, and so on. Here is an example. So suppose you have this initial square wave in terms of the grid cells shown here. Now, so how do you choose? Say you want to do a linear reconstruction. You can the Gaussian output has told you just make it so it's constant. We want a higher order accuracy, so you're sort of willing to go from constant to a linear slope. Now you can choose this slope. So if you calculate the slope of this, you can base it on this difference, or you can base it on this difference. The left differences gives you 0 as the slope. The right differences give you this negative value for the slope. So what do you choose? So you can do averaging and so on. Now, suppose we choose this steeper slope. Okay, so this is reconstruction step done. This is reconstruction. Okay, evolve is just moving it by v delta t. So this is evolve step. And now the averaging step is nothing but you take the average of this portion and the average of this portion. If you just do this averaging, it's actually trivial mathematics. This is what you'll get. You'll get qin plus 1 equals qin minus v delta t by delta x. Again, we have changed the names of variables from u to f to q now. But you have to face this, all the books in different rotation. So this portion is just the burden of flux or the upwind update of it. It's this is what we wrote down, right? You just take the difference of I minus I, right? This is just that part. So this is the additional part which comes from this linear reconstruction. And these sigmas are the slopes. So this is a general expression which is not for the specific case. Let's say if you had an initial reconstructed thing with some average value and a slope, and if you rated it and averaged it, this is what. Okay, so these are the slopes. These sigmas are the slopes. Now you can actually see the problem with this method right here. This was a step function. When you do this REA approach, you have taken out more negative value from that cell and have remained with this constant plus this high peak. Right. Average of this will be larger than the initial value that it. So you have introduced new extreme. This is a new maximum that you have created from this reconstruction, and it's a problem. You saw that Max Wendroff all those oscillations. This is the, this is another way of looking at it. So this is not good. So these slopes have to be chosen extremely carefully. Okay, so these are different, centered up and downward slopes. I'm not going to talk about this part. Defining a little bit in this as well. Now there is a theorem which says that if reconstruction, if just this step is does not introduce new extrema, for example, here in this profile there is a new extremum introduced here. So if the theorem says that even in the reconstruction you don't introduce new extrema, friction will not create new extrema. It's obvious, right? If you don't have this peak here, advection won't create a new peak. So all the effort has to go into making this slope, choose this slope cleverly enough that you don't introduce new extrema in the reconstruction step. Okay. So this is the problem case that I just showed. Now here is another, this is not the same problem, but here is a case where reconstruction does not introduce new extrema, right? This is, it was monotonic previously, and after reconstruction, it's still monotonically decreased. So these are, so the trick to get these slopes is something called limiters, slope limiters. Okay, slope limiters. So basically, for example, here, qi minus qi minus 1. So this is I minus 1. So you take this slope and you take this slope, this I plus 1 minus I. This slope, and you somehow combine this slope and this slope so that the reconstruction is monotonic. Okay, this min mod, for example, is a nonlinear function. So basically, if it's a min mod of a and b, if a and b have opposite signs, or if one of them is 0, you set it to 0. Right. So if the two slopes, so here this slope is 0, this slope is something. You don't do a plus b by 2. The arithmetic average is not good. It will create new extrema. But if you use this min mod averaging, and the reconstruction will in that case just be flattened like this, and it will not give you new extrema. The min mod is not that good. It is non-monotonic, but you can do better. Okay, and there are these MC and Manlier limiters. In fact, there's a beautiful paper written in 1980s by someone called Sweeby in computational physics literature, which actually just shows what are the properties of these limiters which work well for reconstruction. You can actually prove theorems and so on here. But I'm not going to go in detail to this. The idea is what I want. The idea of slope limiters. In fact, these slope limiters can actually also be programmed in terms of limiters of Huygens fluxes. So you have these Godunov fluxes, and now you have these corrections to these fluxes, where the fluxes are limited. This is a reinterpretation of this slope idea, which I'll not go into detail. And this is a demonstration of how to choose slopes. One just do simple averaging. This is an example of advection with limiters. This is what magic happens when you go to these limiters with a higher order reconstruction, like a linear reconstruction. So this is the same problem. And now there are no phase errors, and the amplitude errors are also reduced quite substantially. You can see this on the greenish one, almost very, very good. So yeah, this is a higher order. The code for this is also big. So you should try this out. Okay, so I'm actually running out of time. And this is anyway independent. So this is a little bit of a historical thing that I want to tell you. Zeus was the first astrophysical code which was adopted on large scale by government. This paper, which introduced the Zeus code, this is an open source code in astrophysics. It's written in 1992. So this code was based on finite differences. So it was not conservative. When it was finite differences, so it did not consume things. It's very successful method This was like all clones of Jim Stone's. This unique thing about this code was this is what led to this open source culture. Astrophysics. After this, all the code that came out and became popular were open source. There are no commercial codes in astrophysics. So this is a historical thing now. Now most codes are finite volume. I'm not going to go into details of this. So you can actually see here it ignores the v dot grad v term and solves this in a finite inference way. And then it solves the v dot grad v using ideas of probability. That's really the thing about it. So I'm not going to go into detail. I don't have time. This is the last thing that I want to mention. The idea of operator splitting. Right? So you solve Euler equations, but that's not it. You have to include things like cooling, radiation. You have to include diffusion and so on. So do you invent a new numerical method every time you add these things? The answer is no. You want to use something called operator splitting. So for example, you have two operators A and B, and this is an equation that you want to solve. So dou f dou t equals A plus Vf. A and B can be nonlinear operators, so they can depend on F. If you solve it, and A and B are matrices in general. If you solve it, this is Ft percent of D by Ft is the A plus matrix. That's A. These are matrices, and if you do a Taylor series expansion, you have these terms. Okay. So what operator splitting tells you is don't bother getting a very high order method from doing A plus B together. Instead, what you do is you do A first. So this is just A applied to Fn. Okay, and then to the updated solution apply B. Okay, so the two independently are not that hard. And that's what you do. And if you look at the matrix thing, Taylor series that you get here is this. And you say they are very similar. The error is this. And the error does not vanish in general because A and B being matrices don't commute. So AB is not equal to A. But it is still second order accurate. It's very good. You don't have to work very hard to get this. That's the idea of operator splitting. Since I'm running out of time, this is my summary. And now I think we'll just move on to Dipan will stop.